Hello class, before we are going to get into velocity versus time in this lecture, however, first I want to just do a really quick recap on position versus time. There's really three basic things you need to understand about the position versus time graphs. I'm not even going to put numbers on these, I will label them, but I just wanted you guys to understand some things. Sorry. Here we have as flat of a line as I can draw. Here we have a straight but sloped line, and here we have a curved line. Really quickly pause, think about what each of those means to the position. Alright, so recap. A flat line of position means it is not moving, right? It is not moving at all. It's staying in one position. As time goes on, its position is exactly the same. Looking at the next one, we see that since it's a straight line, this is important. I know some of you missed this on the quiz today. This is velocity is constant. It can be negative, it can be positive. If it was negative, it would be going this direction. It can be positive, negative, but velocity is constant, but position is changing. And the last one, it's a curved line. We don't talk as much about these because the calculations are a little too advanced for this class, but you do need to understand what it means. So we know that it's still going forward and it's going up, so it's positive. Remember, I talked about if it's curved, that means we do have acceleration, right? Not a word to throw around lightly, only on curved lines. Apparently cannot spell that. Acceleration. So it's a curved line, and we know it's a positive acceleration because it's a happy face. If it's a sad face, it is negative acceleration. So this means that the velocity is changing as well as the position. Right? Your slope is not the same the whole time. Your velocity is not the same the whole time. So just keep these in mind as we now start to look at velocity graphs. Alright, so for the velocity of time, it's the same idea, except instead of measuring where it is, we're measuring how fast it's going at a specific time. So for example, if our object is not moving, then our line's going to be along the origin or at zero because, there's no velocity, it's not moving. However, if our object is moving at a continuous velocity, right, at time 1, it's going at a certain speed. At time 2, at time 3, it's going at the same speed the whole time. To correlate that to our position graphs, this would be the position graph for that. Alright, our slope is constant, so that means our velocity is constant. Our velocity does not change.
Jacob Jimenez, come to the attendance office. Jacob Jimenez, come to the attendance office.
Yes, I am making this during the school day, so announcements will happen. Then let's look at, say, this velocity graph. Alright, so try to draw, so this velocity, the velocity is increasing this whole time. So from here, think about what does that mean for the position, the one we're used to. What would the position be? So click pause, try to draw the position graph. Alright, so now that you've drawn your position graph, labels, always write your units, meters, seconds. Alright, so its velocity is increasing. So if its velocity is increasing, remember, change in velocity over time equals acceleration. So that means it's accelerating. If it's accelerating, it starts off moving slowly and then going much faster. This will give us a curved position line. Alright. So really quick, think, what if scratch that, I don't want to quite go that far in this lecture. So we're actually going to even be able to calculate the velocity. Think about how might you calculate the velocity from this? Or how might you calculate the acceleration? Alright, so overview for this. You should be able to, at the end of this lecture, look at its velocity time graph and tell me what's happening. And then use that same velocity versus time graph to find the acceleration, the velocity, and the displacement. Alright, So looking at this graph right here, we wanted to talk about what does it mean to have a positive velocity and negative velocity, and what does this mean for the object. So we don't actually know where it starts. I have my red number line here at the bottom, but we do know that it starts off with a zero velocity right here. There's no velocity, it's not going anywhere, but as time goes on, it starts to go faster, the velocity increases, and it's going faster and faster until it hits this top velocity up here, right, where it goes, and then it continues going at a constant velocity at that time. But then, as time goes on, it's still moving forward, but in this section, right, our velocity is going down. So it starts off large, then our velocity gets smaller and smaller until eventually we have a zero velocity. And then right here under the line, you notice we now have a negative velocity. It was positive but getting smaller, and then once it crosses into the negatives, that means we now have a backwards or a negative velocity that is growing and growing and getting more and more negative as time goes on. So another way to think about this is when the velocity is up in the top part, I'm going to try to shade it in here, this orange area, right there, that's all a positive velocity. So that whole time, your object is going forward, right? However, once you cross over that line, whether that forward velocity is big or small, it's only after you cross over the line here that you now have a negative velocity, or you're going backwards. So remember, in this case, anytime it's above the line, it's still going forwards. It's just not negative yet, right? It's still going forwards, but once it crosses over, then we have a backwards velocity. Alright, so now I want you to think, what would an object have to do to make this graph? So, pause, think about it, and then I'll quickly go over it. Alright, so let's start with the beginning of the graph. I'm going to try to color code this. So we start off, right, he's walking, or whatever the object is going at a really steady 5 meters per second. So we're walking forward, because we are at a positive velocity, right? We are above the line, so it's walking forward or a positive velocity, and it's going to be constant, right? A constant speed, or constant velocity. Then, as time goes on, we're still going forward, however, we are slowing down. So this area is still a forward velocity, or a positive velocity, but we are now slowing. Right? Our velocity is getting closer and closer to 0. Now, if this line were to continue past the 4-second mark, we can assume that if this trend continues, we're actually going to get into a negative velocity, which means instead of forward, we are now going backwards. And as time goes on, it is getting more negative, which means it's going faster in the backwards direction. Alright. Think about it, this won't be the last time we talk about it, but just keep working at it. Alright, so I have these two graphs where I want you to practice with. Right now, I want you to tell me tell me what's happening with each one of these. How was a graph like this made? Alright, so let's look at the first one, right? So we're starting at a 0 velocity, so that means it's gaining velocity, so it's all going forward because it's all in the positive, so this has a positive velocity, and it's increasing, so it's going faster. And then at this point right here, say maybe you're speeding up in your car, and then right at that point you suddenly hit your brakes. You're still going forward, so after that brake we still have a positive velocity, but instead of increasing that positive velocity, we are slowing down until we get to a zero velocity at the end. We have a zero velocity. Alright, then looking at the second one, right, we start with a negative velocity. We're all the way down here. So you start with a negative velocity, and you're getting, and as time goes on, you're getting closer to a zero velocity. So it's going from negative velocity to more of a zero velocity. So think of it, it's going backwards, but as it's going backwards, it was going really fast backwards, and now it's slowing down and it's getting ready to turn around. So say you're reversing your car, say you were doing this quite quickly, and then at that point, oh, you start to hit your brakes, you're getting closer to a zero velocity, and then once you hit this point here, you are at a zero velocity, and then you start to go forwards after that point with a positive velocity. So you're going backwards, you hit your brakes, and then you finally stop at this point, and you hit your gas, and you continue to drive forward. Alright, now that we understand more about velocity graphs, we can use them to find acceleration. So looking at this graph, right, we can see the velocity graph, it's over time. Hopefully from our definitions we remember that change in velocity over time gives us our acceleration. Now hopefully this looks a little similar to you when we talked about change in position gives us velocity. So think back, how did we find that change in position to get our velocity? Hopefully you remember, we got pretty good at today. It was finding the slope. So if you have a velocity graph, you can now find the slope and get your acceleration. So slope is going to be very important, especially in this first section. So let's look at this first part here. So we want to find the slope of this section between 0 and 2 seconds. Hopefully you can look at that and say, oh wow, there is no slope, which makes sense. Right here, our acceleration is going to be 0 meters per second cubed. Now maybe you're wondering how I got at those units. We know that velocity, the velocity at this point is 4 meters per second. We need to find the change in that. So that's 4 meters per second minus 4 meters per second, which will give us 0, but our units are still there, divided by the number of seconds, which is 2 seconds. This 0 meters per second is the change in speed over 2 seconds. So when we have these 2 seconds, they'll combine to be seconds squared over here. So going on to the next part of our graph, this section. So our velocity is changing, so we do have a acceleration, but our velocity is getting smaller. So we're having actually, in fact, a negative acceleration. You can check this by finding the slope. Acceleration, right, we've gone to rise over run, so we haven't risen, we've fallen, so it's going to be negative. We've fallen from 4 meters per second to 0 meters per second, so it's going to give us 4 meters per second negative, and that's happened over a total time of 2 seconds. So divide that, we're going to get negative 2 meters per second squared. Remember, keep your units on this. Alright, so after we find acceleration, we can also find displacement. Now remember, displacement is the change in position, or the change in x, because remember, x stands for position. So I like to think of it both a formulaic way, also just thinking about it. So if we go 4 meters per second, alright, we can figure out how far we've gone if we figure out how much time it's taken us. So if we're going 4 meters per second and we spent 2 seconds going 4 meters per second, how far have you gone? So that means in 1 second we go 4 meters, in 2 seconds we go 4 meters. Hopefully you can do the math, and it's going to be 8. But there's another way to think about it. There's a lot of ways though. A pretty easy one is you got to find the area under, right? Because that's going to give us the 4 meters per second that we're traveling times, although if you were in chemistry you might have seen it this way, 4 meters per second, and we're going to multiply times the amount of seconds. So that'd be 2 seconds. Notice our units here can cancel out. Really, it's true, if your units cancel out, you're probably doing something right, as long as you're canceling correctly. So here, and we're going to get that traveled a total of 8 meters. Then you can just check, right? 2, here's our 2, times our 4. 2 times 4 is 8. We've traveled 8 meters. Or for each second, we've traveled 4 meters in that 1 second. But if we want to find the total displacement, we have to also find the other area. Remember, area of a triangle is multiply the sides against each other and then times 1/2. So this side right here is still that 4 meters per second. The bottom side here is going to be 2 seconds. But since, remember, we're missing half of it, this area here is missing, not here, empty space, we have to times it by 1/2. So you can cross out your S's, cross out your 2's because it's on the top and the bottom, something over itself is 1, and you're going to get 4 meters. If you add up those areas, that's your total area, and you're going to get 12 meters displacement total. So the big key in this is finding the area under the curve. So you need to find the area under the curve. We will definitely work more on this. This is just a quick, or maybe not super quick, this got longer than I thought. But so find under the curve, and we will continue working at this as time goes on. I just wanted to get an introduction to it.